Hi. In units 1, 2, and 3, we have discussed much of the basic organometallic chemistry of the S and P block metals, which, as we could watch in video 1 of unit 1, was understood by the early part of the 20th century. We are starting today unit 4, which is the first one devoted to transition metal organometallic compounds. The organometallic chemistry of the D and F blocks have been developed much more recently. Remember that the first transition metal organometallic, the first olefin complex, was synthesized in 1827, the Theiss salt. However, it was not until several years later that the real structure was elucidated. The first binary metal carbonyl was obtained by Lemont in 1890 by serendipity, and some other D-block organometallics were also synthesized in the 19th century. Anyway, it was not until the discovery of ferrocene, an extraordinarily stable organometallic compound, that the organometallic chemistry of transition metals really blossomed. In this unit 4, we will start with some structural and electronic characteristics to go on with the rule of 18 electrons, which will be basic during the rest of the course. We will highlight some exceptions, and we'll finish the unit with what it has been called the isolobal analogy. Let's remember that transition metals have a number of electronic characteristics that make them different from those of the main groups that we have just seen in previous units. In addition to the S and P orbitals, these elements have D orbitals available, and therefore more complex organometallic compounds will be formed. The bonding in organometallic compounds of the S and P blocks is often relatively simple and normally is described by sigma bonds. The D metals, in contrast, form a large number of organometallic compounds with many different bonding modes. The transition metal has the ability to donate electrons and, in addition, to accept them, since the D orbitals can be empty. The variety of organic fragments in these compounds is virtually infinite. Alkyl substituents, alkynes, carbonyls, aromatic and heterocyclic compounds. Some may not only donate but also accept electrons. The nature of the chemical bonds in these compounds is expanded by a wide variety of possible situations. Organometallics with sigma donor ligands, metal alkyls and aryls, organometallics with sigma donor pi acceptor ligands, such as metal carbonyls, organometallics with multiple metal carbon bonds, for example, metal carbene complexes, organometallics with sigma donor pi acceptor ligands, such as olefin complexes, metallocene, arenes. These hybrid, usually partially occupied orbitals can interact with bonding and antibonding pi orbitals of unsaturated organic molecules, both donating and accepting electron density. Certain ligands such as carbonyls, olefins, arenes, etc. can donate electrons to the metal and can also accept electronic density from it. Electron donors sigma or pi type and can accept pi type electrons, producing what is known as synergism. Synergism is the total effect of the donor-acceptor bond is greater than the sum of both separately. The oxidation states of transition metals are very varied, and the metal orbitals can be hybridized, giving rise to a wide range of different coordination geometries and coordination numbers ranging from 1 to 8, of which 4, 5, and 6 are the most typical. A metal from the main groups, such as tin, uses its 4 valence electrons for the formation of 4 sigma bonds. The result is a stable molecule like tetramethyl tin. The stability of the tetramethyl tin and the instability of, for example, the trimethyl tin can be predicted by the octet rule, which says that when the number of bonds formed around the central atom is such that it forms an octet of electrons, the element reaches the electronic configuration of a noble gas. Well, for transition metals, the 18 electron rule allows a similar prediction. 18 electrons are needed to fill the 5d orbitals, 1 s orbital, and 3 p orbitals of a transition metal. The 18 electron rule says that a stable complex is obtained with the electronic configuration of the following noble gas when the sum of the d orbitals of the metal, the electrons that the ligands donate, and the overall charge of the complex is equal to 18. It is a predictive rule. It allows to predict the stability and structure of organometallic compounds. By counting the number of electrons in the outer layer around each metal atom in a complex, you can predict not only whether the complex will be stable or not, but that in some cases there will be metal-metal bonds, and whether the ligands will form bridges or will be terminal, among others. It is usually fulfilled among organometallic compounds, especially among those with carbonyl and nitrosyl ligands. The relationship between the stability of organometallic compounds and the 18 electron rule can be understood by reviewing the description of the bond in the complexes according to the theory of molecular orbitals. And thus, in an octahedral compound, the most stable ordering will be one in which all bonding orbitals, these ones here, are fully occupied and all antibonding orbitals are empty. As there are 9 bonding molecular orbitals, 18 electrons are required, as predicted by the 18 electron rule. Therefore, complexes will comply with this rule when they have high values of delta octahedron, which causes that the occupation of the antibonding, e.g. antibonding orbital, is not favored.